The column for this azeotropic still is a 1.5 metre piece of 28mm copper pipe. You also need a short length, a metre or so is plenty, of 8 or 10mm copper tubing. You can make it with just those things and one exit from the column, but you get better vodka if you add in a PID controlled thermostatic column extension and a liquid extraction point. The column has a downward sloping piece of 8mm copper tubing coming out of the top. This pipe will act as an air-cooled condenser, and on my first column I used a piece of pipe that was about 1 metre long. In operation, the large majority of this pipe was cold to the touch, so 30 to 50 centimetres would be quite long enough. My design differs from most moonshine stills in that it is a fractionating column designed to separate two distilled fractions, heads and hearts. One reason for doing this is that the column is designed so that it can be used for continuous distillation, where fractionation is the only way of separating heads and hearts, as cuts can't be taken. The other reason is it's a better way of separating heads and hearts than cuts, giving a better quality vodka with lower losses to the heads. Even though a conventional moonshine column is not called fractionating, it does separate wash into two fractions, bottoms and top, and only the top fraction is removed as vapour. The same is true of a fractionating column. There may be draw points at various stages on the way up, and only the top fraction is removed as vapour. All other fractions are removed as liquid. So, above the main column there is a liquid draw mechanism, and above that there is a further extension of packed column with a vapour exit path at the top. The column extension contains less vapour than the main column, and there is insufficient vapour to keep it hot, so it has to be externally heated. The proportion of the distillate that exits the column as heads versus hearts is determined by the column extension temperature. This is a graph of some measurements that I made. With temperatures over 75 degrees centigrade, the vapour all comes out as heads. Under 65 degrees it all comes out as hearts, neither of which gives separation. I did a video on this topic explaining the relationships between temperature, proportions and taste. I recommend using a temperature of 70 degrees centigrade, giving a ratio of approximately 1 part heads to 10 part hearts, but this may vary slightly with your own altitude and column. Little vapour needs to pass into the column extension, so it does not need to be as wide as the column. With low vapour flow, there is insufficient vapour to keep the temperature of the extension constant, so we end up with this arrangement of a 15mm tube extending above the column with a water-jacketed heating system that consists of a 200mm piece of 28mm pipe with a heater at the bottom and a temperature sensor at the top inside the column rather than inside the water jacket. This can be made with fittings such as 15 by 15 by 28mm T-connectors, but these are bulky and expensive. I soldered it up with pieces of pipe and sheet copper. Happily, the UK's sterling 2p coin fits exactly inside 28mm copper pipe. If you cut the pipe with a pipe cutter, then the burr on the inside is just right to hold the 2p coin in place for soldering. You need to drill holes in the 2p coin to admit the 15mm copper pipe, and then you need to add another cap to the 15mm pipe at the top with an 8mm hole to admit a piece of 8mm copper pipe to act as a thermal well for the PID temperature sensor. This well is closed at the bottom by crimping and soldering. Other complications are that you need to have a clear piece of silicon rubber tubing connected to allow the level of water in the chamber to be viewed. And you also need to take an 8mm piece of pipe that's soldered to both the 15 and 28mm pipe so that it conveys the heads vapour from the column through the water jacket to the outside without losing temperature while it's inside the column. It's this piece that wants to be 30 to 50 centimetres long. As with any water jacketed temperature controller, it needs to be heated at the bottom so that convection currents carry the heat upwards. You need a PID controller, and I use a PT100 platinum temperature sensor. There's a bit of fiddling around following the instructions of the controller to set it up to the right type of sensor, and then you need to put it through a self-tuning routine to optimize its parameters. The PID controller is set to 70 degrees centigrade. I insulated my column extension because I'm using a relatively low power heater and live in a cold climate. If you live in a warmer climate, you may find that you need more cooling in order to keep the temperature where you want it, as the vapour may heat it too much, so some experimentation with insulation may be required. I leave a 50mm gap of bare 15mm copper pipe below the water jacket in order to allow for the transition in temperature between the top of the column proper and the water jacket without too much cooling of the top of the column by heat conduction through the 15mm copper pipe upwards. PID controllers are available commercially for a few dollars. PID stands for Proportional Integral Differential, the derivatives of the sense temperature that are used to control the heater. There are plenty of YouTube videos about how they work and why they're better than thermostatic controllers, but for this application it has to be a PID. A thermostatic controller does not get the temperature stable enough. You need a heater power of at least 50 watts. I used 2 small silicon pad heaters, but that added another complication because they were 12 volts, so I had to add a high current 12 volt DC power supply and rig up a circuit with an IFR350N MOSFET to control it, rather than a solid state relay that PID controllers are designed to work with. Instead of silicone pad heaters, I recommend using these band heaters. They are cylindrical clamp-on pipe heaters used to heat the nozzles of plastic injection devices like 3D printers. They have generous power of 100 to 150 watts and are driven from mains voltage of 110 or 220 volts AC, so you use a solid-state relay rather than a MOSFET to control them. The relatively low power in this application means you generally won't need a heatsink for the solid-state relay as long as its metal base is not insulated. But if it's mounted metal side up, you won't be able to see the LED. If you want the extra security, then I suggest you mount it on a heatsink. Band heaters are inexpensive, but they don't come in 28mm sizes. They come in brass and stainless steel types. I've only used the stainless steel ones because they're a lot cheaper and they seem to be more flexible. They come in 25 and 30mm diameters. The 30mm ones will tighten down to just over 28mm and can be made to fit by cutting a piece of copper sheeting from a copper pipe and wrapping it round as a conductive spacer between the heater and the 28mm pipe. The 25mm heaters won't quite stretch wide enough for a 28mm pipe. Once it's all rigged up, you fill the chamber with water, turn on the PID controller and put it into programming or training mode. That's a machine learning mode where the controller works out the best parameters for the application, depending on how fast the thing heats up when the heat is on, how much it overshoots the desired temperature, etc. Then once it's trained, it will revert to PID mode and generally will give you accurate and constant temperature. Between the column extension and the column proper is the product collecting system. It's composed of 2 diagonal plates of copper overlapping each other so that any drips falling from the upper one land on the lower one and are directed out of the exit port, while allowing vapour to pass up between them. The dimensions here are not critical. I made 2 cuts in the column tube with a standard hacksaw at approximately 45 degrees, each passing about 60% of the way through the diameter of the column, spaced by a vertical distance of about 15mm. I made copper sheets from 15mm copper tube cut along the side and flattened, and I pushed these sheets into the cuts and soldered. For the exit port, I drilled an 8mm hole in the column just above the lowest part of the bottom sheet and soldered in a piece of 8mm copper pipe. The exit port is intended for liquid only to escape and so requires a U-tube to prevent vapour escaping. This is the only U-tube employed in the azeotropic pot still. And it works okay if the U-tube's depth is about 35mm, but that's assuming you've got it tuned up and working. The process of tuning it up is quite fiddly, and one of the frustrating aspects is malfunctioning U-tubes. When working out the optimum column operating parameters, you are likely to have higher column pressures that will blow any liquid out of a short U-tube. To begin with, you want a deep U-tube in which you can see the level of liquid, but what I eventually hit on was using the Parrot as a U-tube. It's slightly awkward having it so high up the column, but it's ideal for the U-tube, partly because it's deep and partly because the inlet side is narrower than the outlet side of the U-tube, making it almost impossible for high vapour flows to blow all the liquid out of the U-tube. It's also naturally open to the air. One final minor point is that as the still is to be run for many days, there can be an appreciable amount of alcohol loss via evaporation from the exposed surface of liquid in the parrot. To minimise this, you can attach a flat board around the top of the parrot, onto which you place an upturned glass or jam jar to minimise alcohol losses to evaporation. In the next video, I will discuss making the column proper.